Hi, it's Mr. T here. In this video, we're going to look at the reactions of alcohols and haloalkanes. Now, I have over 20 years experience teaching chemistry, and I think that there's some really important things that we can learn from this video about alcohols and haloalkanes to help us pass our exam. Okay, so how do you get ready for studying organic chemistry? Me, it's a bit like the little dog there, though I don't get nervous when I have my cup of coffee. Okay, let's have a look at some reactions of alcohols. So generally in this part of the video, we're going to look at the three important reactions of alcohols. We're going to look at oxidation of alcohols to carboxylic acids, substitution of alcohols to haloalkanes, and the elimination of water from alcohols to produce alkenes. So those are the three types of reactions we're going to go over. The first, also remember from the last video that we had alkenes could produce alcohols, so there's actually reverse reactions that could come into action here, but we're not looking at those during this video. Okay, so the first reaction of alcohols, the type we're going to look at, is oxidation. We can undergo, well, we're going to look at primary alcohols mainly, not secondary or tertiary in this video. So, and we can do those oxidation reactions by adding two different reagents. The first reagent is permanganate, and it's acidified. Now the permanganate is this MnO4-, and the dash here with the H+, is the acid that's been added, which is why it's called acidified permanganate. So we're going to add acidified permanganate to an alcohol, a primary alcohol. Notice here, here's our alcohol. It's not written OH, it's written HO or HO. That's only because the carbon directly bonds the oxygen, directly bonds to the oxygen to the hydrogen. So sometimes you'll see it written like this, and sometimes it'll be an OH, or sometimes it'll be an OH if it's written on the right hand side. Just be familiar with that type of representation. So we've got the alcohol group. It's reacted upon by this reagent, this permanganate. So the permanganate is an oxidizing agent. It's going to reduce the alcohol to a carboxylic acid group. So our major change here in oxidation is this OH group, okay? The hydroxyl group is changed into the carboxylic acid group on the same carbon. It happens at the same place on the organic molecule. So the other type of reagent we can use, which is a very similar type of reagent, it's an oxidizing reagent. It's going to make the same change, but we're using a different reagent. It's called acidified dichromate. So dichromate is Cr2O7 2-, and the acidified bit is the /H+. Notice here I've drawn the OH on the other side. So here's our alcohol group. We're going to add our reagent, and we get the carboxylic acid. So notice what's actually happened is this carbon here has lost its two hydrogens and it's gained a double bond oxygen. And that's the same that happened here. The carbon that's attached to the OH lost the two hydrogens and gained a double bond OH. Now this reaction is important because it's actually, these two reactions are a test for alcohols. So at this level, at level 2 chemistry, we use this these two reagents to test, and if the reagents actually, we notice a color change, we say that there is an alcohol present. So an example of this is we take a sample of an alcohol. We're going to do the acidified dichromate test here. We add some acidified dichromate. Notice it's an orange color to our solution, and we get this orange color. We give it a shake. The orange color stays, it's present in the first few seconds. So we put it in a warm water bath, and we heat it for 5 minutes. Now what we'll notice, it'll go green or blue. Now that test, that going from orange to green blue, is a positive test for an alcohol being present. It's also a test for another type of organic compound, but not one that's important in level 2 chemistry. So the test can be used to identify for the presence of alcohols. The positive test, you would say here, there is an alcohol if the solution changes from orange to blue-green, then an alcohol is present. So we do a second test that we use to test whether an alcohol is present in an unknown sample. We take another unknown sample, we can add something called the acidified permanganate, that's the MnO4 minus, with their H plus being added, the acidified part. We add that to the solution, the purple colour goes into the solution, it turns purple, we put it again, we heat it, and after 5 minutes we get it going colourless. So this test is used to identify the presence of alcohols as well, but in this case the solution changes from purple to colourless. So if you have permanganate and you add it to your sample and it goes from purple to colourless after a wee bit of heating, we know that there's an alcohol present. So the second type of reactions that alcohols undergo are substitution reactions. So an example of substitution reaction here is when we react the alcohol with phosphorus pentachloride or PCl3 or SOCl2. Now these samples all have excess chlorines in them, and it's actually the chlorine that replaces the hydroxyl group here, or the OH group. Now notice when the alcohol group has the reagent, PCl5 in this case, added to it, the chlorine will replace exactly where the OH group was attached. So if it was attached to the second carbon, the chlorine is put only on the second carbon. Now this is true for all organic chemistry. So when we do these changes to functional groups, the change happens at the place where the old functional group was. So we're replacing something on the, attached to the second carbon with something new. This is a substitution reaction. We can also carry out this substitution reaction here with hydrogen halide, like hydrogen chloride, hydrogen fluoride, hydrogen bromide, or hydrogen iodide. So you can use either one of those and add them to an alcohol. When you add those to the alcohol, you get this hydrogen, you get the halogen part there adding to where the carbon was. So it's the halogen that replaces the OH, sorry, where the OH was. So the halogen replaces where the OH is. And because now that the OH has been taken away and we had a hydrogen that was left after we gave away the bromine, we also produce water at the end of this reaction. Also notice at the top here, I forgot to say before, that as well as producing the organic product, each one of these reagents actually produce its own non-organic product. Okay, so the third type of reaction that alcohols undergo is called an elimination reaction. Now, elimination reaction is where something is removed, and in this case, for an alcohol elimination, we're going to remove an OH and a hydrogen from adjacent carbons, carbons that are next to each other, and we're going to form a double bond. So let's have a look at how we do that. Now, concentrated sulfuric acid is what I add to make this happen. Concentrated sulfuric acid has a huge affinity for water, so it will find and take water from anywhere it can. So if you add it to an alcohol, it's going to remove a water group, an OH from one carbon and an H from the next carbon. So have a look here. Here is our hydroxyl group. It's going to remove that, and it's also removed this hydrogen on the other side here, and it's produced an alkene. So we remove the hydroxyl group and the hydrogen, we make the alkene, we also produce water. Okay, there's water produced, but the sulfuric acid just sucks that away. So a problem that we have when we're undergoing these elimination reactions is we can potentially get a molecule in the form of this one here, this butane 2-ol. Now we can see that if we add the concentrated sulfuric acid, we're going to remove a water. However, there is two choices available here. I have to remove the OH from the second carbon, but the other hydrogen that I remove has to be from an adjacent carbon. So it either can be one from this carbon or this carbon. So which one is the one that we should remove? Is it the one from the first carbon or the one from the third? Well, Zaitsev came up with a rule to say that the majority of the time one will happen more often than the other, and this is called Zaitsev's rule. So it helps us eliminate what the major product is, to identify the major product from these elimination reactions. So what is Zaitchev's rule? So it's similar to Markovnikov's. In fact, it's kind of an opposite to Markovnikov's. So Zaitchev's rule is the poor get poorer. That is, the carbon with the least hydrogens, that's this one here, will be the one that forms the other side of the double bond. So the first side forms where the carbon is joined to the OH. The other side will form to the side that has the least hydrogens. That poor get poorer. That is the majority of the time. Remember, there will still be a small amount, a minority that happen on the other side. So you will get two different products, but you'll get the product, the majority product will be when the double bond forms on this left-hand side here, or in the one that joins to the poorer hydrogen. So this is called Zaitchev's rule. Now, what I mean by the poor hydrogen, look at the bottom here. You can see that the carbon on the right here has three hydrogens attached to it. So it's the richer carbon because the carbon on the left has two hydrogens. So this is the poorer carbon. This is the one that is going to lose its hydrogen. Okay. So stop the video now. Get yourself a piece of paper, get yourself a pen. And what I want you to do is draw the following reaction map. I want you to draw the molecules that come from each of these reactions. I want you to draw their names and write down the type of reaction, just as a check to see whether you've actually learnt the work that was in the previous part of the video. So I'm going to start this video again in about 5 seconds. Okay, so if we look at the three reactions here, the first one down the bottom here, let's just do this one first. We've done an elimination reaction. We took away there was only one choice here because the OH was on the right hand side, so we've produced that. We've done an oxidation reaction with our dichromate, and we've produced carboxylic acid where the alcohol was. And our PCl5 is going to be a substitution reaction. It's replaced the hydroxyl group, the OH group, with the Cl. So you just need to pause here again and check whether all of your structures and naming is correct. So let's have a look at the reaction of haloalkanes. Remember, haloalkanes are organic compounds that have a halogen attached to a carbon chain. They can be chlorine, a bromine, a fluorine, or an iodine, and they are the haloalkanes. Oh, remember, sometimes instead of putting the chlorine, fluorine, bromine, iodine, we put an X down to denote that they're a halogen. So they can undergo substitution reactions with potassium hydroxide in aqueous solution. That means it's dissolved in water to form alcohols. They can undergo substitution reactions with concentrated ammonia or just pure ammonia to form an amine, or they can undergo an elimination reaction. Now note, this is also potassium hydroxide, but the elimination reaction produces alkenes. Now, because this is an elimination reaction, we could have Zaitchev's rule in operation here. We could have a major and minor product. So we're going to look at these three types of reactions more closely, 2 substitution reactions and 1 elimination. Okay, so let's have a look at the reactions of haloalkanes. The first type of reaction we're going to look at is the substitution reaction. And the substitution reaction happens very commonly with alkyl halogens because the halogen functional groups are very reactive. So they're very easy to be removed, and because of that, they make halogens a very good starting point for many organic reactions. So if you're going to produce an organic product, often you'll start with a haloalkane. So the first reaction is we add ammonia or concentrated ammonia to the solution, to our haloalkane. So what happens here is the haloalkane part, the functional group, is replaced by an amine group. So the ammonia loses a hydrogen to become an amine, NH2, and that attaches where the halogen was attached. So it's a substitution reaction. It's replacing. Now you'll notice here that there's a chlorine and a hydrogen unaccounted for, so that will produce a product of hydrochloric acid as a byproduct. Okay, so we can also add this potassium hydroxide that is aqueous. That means it's dissolved in water. Sometimes, however, it's just written as OH minus aqueous because potentially sodium hydroxide could do the same thing. So if you add that dissolved in water, it also undergoes a substitution reaction. But this time, what is substitute this, I mean the chlorine is still substituted, or the halogen here, but what replaces it is now the OH. And so of course, because we've replaced a chlorine with an OH, we now have an alcohol because we have a hydroxyl group attached to the carbon chain. Again, and I'll keep saying this again and again, whenever we undergo these substitution reactions, the reaction happens at the carbon where the functional group was, at this second carbon here, at this carbon here. This is where the reaction, none of the rest of the molecules changed by this reaction. Right, the last type of reaction we're going to look on in this video is the elimination reaction of haloalkanes. Now, we're going to use this similar reagent to the substitution reaction we had for the haloalkanes, and that is we're going to use potassium hydroxide. However, this time the potassium hydroxide is dissolved in alcohol instead of water. When we dissolve it in water, we produce an alcohol. When we have it dissolved in alcohol, we produce an alkene. Now, an easy way to remember this and not get confused is if you have potassium hydroxide dissolved in alcohol, you can't produce the alcohol. So you can't produce the one it's dissolved in. So it's dissolved in alcohol, potassium hydroxide. So instead of doing a substitution, it does an elimination reaction. What that means is it's going to eliminate the chlorine. Okay, so it's going to take away that halogen group, or if it's a bromine or iodine, and the adjacent hydrogen. And remember, if we use Zaitchev's rule, we had a major and a minor product. So if we look, this is the rich side here, and this is the poor side. There are 2 hydrogens here, and there are 3 hydrogens here. So we're going to take away the hydrogen from the poor side and join the double bond. This happens the majority of the time. We also get this happening as a minority of the time, as a minor product. Now, most times we're only ever asked to give the major product. But if they do ask you to give both products, and sometimes they ask you to give both products and explain why you get both products, you will have to be able to do that. Now, just take note here, there is one other product that actually isn't shown on here. Okay? So there's one other product. So can you recognize what it is? Look at this one here, this major product. It is a cis isomer. So you could potentially also get this major product could produce 2 different of its own products. It could produce either a cis or a trans. So when this reaction happens, it could produce 3 different products. And organic reactions can be complicated like that. So just be on the lookout. So if you ever get a tricky question, is there something more that you need to know about it? Usually you just have to give the major product, but they might ask, could you identify all the products? So look out for that if they're asking you tricky questions. So notice here also that the HCl has been removed, so it's going to produce hydrochloric acid as well. Okay, so pause the video now and write down this reaction scheme. So this reaction scheme, write down where it is now, and then go ahead and put the answers. Put down, name the molecules, sorry, draw the molecules, give their names, and write down the types of reactions, just to see if you've learned the 3 reactions we just went over. I'm going to go through the answers, so unpause when you're ready to want to see the answers. So the first answer here is of course, we add KOH aqueous and we get the alcohol. We add the ammonia, we get the amine. And if we add the KOH alcoholic, we get the alkene. But there are 2 products, there's a major and a minor, because of where the Cl is, the chlorine is joined here. It's joined to a poorer and a richer one. Okay, so what we've learned, if you've watched the video before this and this video, is we have a whole bunch of different reactions that we have now learned, and we can put them through together into one big scheme. Now, just don't get too worried about this, but this is what the big scheme looks like. We learned about all the alkenes. We said that they had 4 different types of reactions, but they were all addition. Addition to make alkanes, addition to make polymers, addition to make haloalkanes, and addition to make alcohols. So that was what we went over in the last video. In this video, we've looked at the alcohols and we've said, okay, the alcohols also have their own sets of reactions. They have an oxidation reaction to make a carboxylic acid. They have a substitution reaction, which is a new type of reaction, to turn into a haloalkane. So we can get into a haloalkane in a couple different ways. They also had an elimination reaction that they could go back to an alkene. So you could add something to make an alcohol and you could eliminate it to get back to an alkene. We also saw today another couple of reactions from the haloalkanes. We can go from a haloalkane and we can eliminate stuff to go back to an alkene. And we can also substitute the halogen group to go back to an alcohol. Or we can produce a new compound, an amine, where we add concentrated ammonia. So all of these actual reactions can interplay with each other and interact with each other. And you have to be, part of organic chemistry is remembering this map or this scheme of reactions. And what I'm going to do in my subsequent videos or the next videos is we're going to go over pose some different problems using this map or this framework to solve, as a tool to solve all the problems. Okay, I hope the video has been useful. So how do you feel about writing organic chemistries at the moment? Do you feel like this dog here performing in front of everybody? They're trying to do like about 4 things at one time. Answer the questions here. Click on the card, answer the questions, let me know. If you found that there's a lot of interesting information in here or you found the video useful, please like, subscribe and share. And thanks for watching the video.